My name is Rafal Szczesniak. No, you don't have to repeat that. This talk is an indirect result of the SMB3 encryption project we done last year at Isilon. And actually, I have submitted the talk as an SMB talk because, after all, we've been doing SMB work. But granted, the idea is generic enough so that instead of being part of the SMB track, I've ended up in one of the last sessions. Thank you very much. But last but not least, well, I mean, technically speaking, I'm not the very last one, but close enough. So let's get started then. How many of you are familiar with anything about zero copy? Good, that's a start.
I'd say yes, but zero.
How about one copy? That one I'm just making up. So let's level the ground before we build some context. What does typical communication of the user space process with the network look like? We get the BSD socket that we are bound to. We receive the data. Through the kernel, the data arrives over the network interface. That's in the kernel. We get that to the user process. It's being copied. We do some processing, do the write to the file, for instance. Then that obviously means we have to copy into the kernel, and on and on. So lots of CPU cycles are lost just to do the copying itself. And in brief, it looks like that. We get the network interface. We receive something. That buffer lives in the kernel. We don't really have access to it yet. Then we actually read off the socket. So we get that buffer in the user space in our process. We do some fine processing. Possibly the amount of data that we are going to deal with further is slightly lower because we've processed the headers, the requests, things like that. So then we do the write into a file, and then again, this is copying into the kernel space, and that's how the data ends up in a file. So copying, copying out, copying, copy out. Painful thing. This is becoming even more painful as the networks that we're dealing with today are becoming faster and more reliable because we are allowed to send more and more data in one piece, not just the header. So right now with MTUs exceeding megabytes, the proportion of copying, the CPU time spent on copying to the actual processing is quite vast. So what do we do? We try to do the zero copy, which means we are trying to attempt wasting the CPU cycles spent on copying alone. That typically means we are trying to somehow access the buffers received off the network or read from the file, keep them in a kernel, and just do some kind of magic in user space, use a few tricks so that we don't really have to see the data. We can just connect certain things and let the syscalls request that, oh, please get the data from the socket and save to that file, or the other way around. Usually that means utilizing file descriptors for doing this sort of tricks, and there are various implementations among the operating systems. The very first one, and that's been a long time ago and it's still there, is Linux Splice. It requires involving a pipe, two file descriptors that belong to a pipe, which means for every single operation like that, you still have to have those two extra file descriptors, which may be a limiting factor. And that's primarily because how pipe buffers work in a kernel, so that you can effectively steal some of the buffers and use the ref counting just to shuffle them around without really copying. But again, that's the Linux-specific syscall. There is also zero copy done by the means of sendfile. Sendfile is involving mapping, which means typically mapping a file so that we can access that in a kernel. Sendfile obviously sends file. It cannot receive. There are implementations of that, although sendfile, as far as I could see, is the most common one. Receive file has certain flavors, but that's irrelevant here. Still, we rely on either being able to use pipe file descriptors or mapping something in order to do the job. So, how does the kernel do that? And by the kernel here, I mean FreeBSD kernel, because Isilon clustered solution, 1FS, is based on FreeBSD, so that's how we started the work. The kernel-level structure called mbuf is involved when it comes to operating on sockets and receiving data off the socket and sending it back. It's a very simple structure, primarily a pointer to a buffer in a kernel space. It has a few fields related to the network itself because it helps to do the IPC communication over the SD socket, which essentially is going to also include the network communication. So there are certain flags, but overall it's primarily just a buffer. However, those buffers can be chained together. Those buffers can be chained together, and that's how they can form a list that can be sent over the network socket. And not only just a list of one mbuf chain, one mbuf list, it can also be linked to another chain, and therefore it can form a packet queue. Still, that's strictly in the kernel. So how could we try to use that? We could try to use something called IO vector, which would follow the same pattern. It would still involve the list, the chain list of entries. Those entries would represent memory buffers somewhere. Oh, by the way, if you have any questions during the talk, please interrupt me. This will make it more interesting. So we can get those lists of entries in the user space. But not every single entry can be treated the same way. So we can have different characteristics depending on what kind of entry we're dealing with. So let's start with something simple. We have an entry that represents an element in a single linked list. It has certain type, more on that in a moment. It has size, it has data of certain length, very simple thing. And the IO vector itself, well, first, last element, pretty simple. That's how we get the structure in the user space. So the very first type of entry, obviously, would be the memory buffer. Simple thing again, nothing horribly inventive. A memory buffer pointed by using a pointer and size. Allocated in user space. If it's allocated in user space, then every time we're going to do something with the syscall, it's going to be copied in and converted to an equivalent of an mbuffer. And that's it. So far, very simple. We're just extending this structure with variable length field like this one, data. So a user space in representation of mbufs. Effectively. So now with the kernel, how would we do that? I mean, the kernel entry would obviously represent something that lives in the kernel. We don't have direct access to it. We cannot really touch it. So if it's not accessible from the user space, we don't need it copied to the user space when we are dealing with it. So if it's passed down to the kernel, through a syscall, then there is no need to do the copy in, copy out of that thing. However, how do we access that thing if it's not in the user space? Anyone? There's a quiz element in it. No one, really? I just told you about the Linux solutions. File descriptor. We have a file descriptor, which we can use to do all sorts of clever tricks. So we have another creature called entry kernel. That creature does not hold data directly. It has the file descriptor. If we have a file descriptor, then that means, yep, there we go. The file descriptor is going to require an equivalent of struct file in the kernel. And it can be pretty much anything. So if we can use an mbuf chain and make it into a pseudo-file that we can, inside the kernel, of course, we can read and write. And reading means just splitting a few mbufs off the front of the chain, or writing means appending them. Then we have something that resembles a file in the kernel space. So that means, and of course, we can send receive if we provide this kind of function. So with this trick, using struct file with a few file ops in the kernel, we can mimic a file inside the kernel, basically. So that those operations are possible. So the FD that we have now points to something that lives in the kernel and is just a chain of mbufs that pretends to be a file. Now, how do we use it? First of all, it's very convenient to use, as it turns out. We can shape create the packets as we go. There is no need to allocate a buffer, for instance, when we are creating a packet that's going to be sent over the network. We can take it step by step. We can create first the header in the user space, set certain properties like flags, session IDs, things like that. Then we can add a request or response, actually, in this case, referring to it, and then add the data read from a file, and just build the chain as we go, which then can be sent over the network. And that's common in SMB space, if we need some padding bytes, then yes, of course, we can just create an empty buffer, attach, and there you go. With no need to mbuf or memory moves or anything like that. So it's very convenient to do. And if we think of it this way, then we just, is it clear enough for everyone, by the way? Okay. So we can just create the IO vector over here, an empty one, and then using IOV create memory entry, just create header, the response, the data one by one, attach it to the linked list, and that's how we build the packet. If you imagine responding to a read request, then in this particular case, we would just use the kernel entry. That would be passed down to the syscall reading from a file, and that file read would effectively just write to that kernel entry, which means that the chain of mbufs in the kernel, and we don't see that data read from a file ever. We don't need that. So this means we build effectively the read response, and the vector can be sent over the network. And that's how the packet builds look like. Again, 2 memory entries, 1 kernel entry that points somewhere in the kernel using the file descriptor to the data that we have just read from a file. Now, on the receiving end, it's useful to be able to chop certain parts off the IO vector as we receive them. We receive something, I don't know, 4 kilobytes of a packet. We know what to expect, so we can split off the header first, we can split off the for instance, write requests, and then just deal with individual pieces as we go. That includes releasing them if they are no longer needed, because after we have dealt with the header, we really don't need it, so we can release that. If needed, the kernel entry can be pulled up to the user space, because there may be cases where we're not certain if this is a write request or not, but we have to be sure before we even touch any pointer. We have to be sure it exists in the user space. Otherwise, of course, segfaults and all sorts of nastiness happens. So we need to pull up certain amount of data into the user space, and there's a possibility to do that with kernel entries, which effectively means converting part of it or all of it into a memory entry that's going to exist in the user space. Yes, there's a downside of it. Syscalls are required. With 1FS that Isilon is developing, we effectively control the entire system, so we get to choose what gets into the kernel or not. But there's a few interesting ideas, more of that later. So let's receive something. We have the SMB2 header. We just pretend we have received. Of course, you don't try to compile this code. This is just the idea. We have received the I/O vector from the SD socket that represents the connection. We pull up the necessary amount of data to represent the header, split it off because the rest of it is going to be used later, and then we just get the pointer that stands in front of the memory entry, so that we can actually cast it into a pointer to the header and manipulate actually analyze and find the session, things like that. Again, this is SMB example. I'm here from the SMB world, even though this is not an SMB track. So, what if we could replace a classic memory buffer that we're going to pass to receive, write, read, and calls like that with an I/O vector? This way, we could request certain parts of the data that we receive or read from a file to be kept in the kernel, because we don't need it yet. We may need it later, but not yet. So if you imagine having those syscalls replaced with, imagine implementing the equivalents that can handle the I/O vectors, the very interesting things are becoming possible. Okay, so how about a few use cases? Large SMB2, right. We have an mbuf. Oh, by the way, with this, just to make it clear, if we use the I/O vector in this kind of syscalls, then we can request certain parts to be kept in the user space in advance, certain parts in the kernel. So in a way, we can request certain geometry of what we are going to read off the socket. And that's actually internally how it's called. It's geometry of the I/O vector. So again, back to the example. We receive SMB2 write, which is large. The large MTU has been negotiated before, so let's imagine we have 2 megabytes, right? We receive it read it off the socket to an I/O vector. An I/O vector is just one tiny piece in the user space that's going to hold the header, and the rest is in a kernel entry. We don't know what it is yet. We don't care. So just don't copy it in copy it out to the user space. We don't need that yet. We'll find out in a moment. The header of the of the request says this is the write, of course. So if that's the case, we know what's the fixed part of the write request, so we can pull it up. And at that moment, the part of the mbuf representation of the kernel entry becomes the memory entry in the user space. We can pull it up. And those mbufs are gone because they've been converted to the user space entry. So you see how pull-up is useful. After we have pulled up the header and the request, we know what we're dealing with. We can split it off. It's no longer needed. Now we have just the file data itself, which can be passed down to the syscall writing to a file, which is good because we don't really need it in user space. So fine, let's just get those 2 megs of data or 4 megs of data in the kernel, keep it in the kernel. Okay, this has been read off the socket. This is the file. Please just shuffle it in. Of course, we can free what's no longer needed because the header and the request. We've done processing the packet, the request, so this can be freed. Right, like I said, can be the mbufs that were received, they will essentially be moved to the file representation. There is no copying involved inside. You can just detach the mbuf chain of the representation that we have in the kernel and attach it to the file. Yes, I'm simplifying. There's a lot of locking involved and tricks like that, but that's the general idea. So we got the data written to the file, the data that has never seen the user space. We have never pulled it up. We did not need to because this is the user data. We don't really care. The packet that we are receiving initially can be saved in a minimum size necessary of IO vector, which means that we have just a tiny header in front, and we keep the rest in the kernel. We will decide what to do about it later as we find out more. And of course, what's been processed earlier in the cycle can be released because we no longer need it. So for instance, if you imagine you have a SMB execution context that holds all sorts of data about the individual requests, if we copy the amount of data that is found in the header, we set those session IDs, flags, tree IDs, file IDs, things like that. Well, not from the header, that wouldn't be a file ID, but that's an SMB specific thing. Then we no longer need it. We can release it. We can save memory. Next case. SMP3 decryption. That's how it started. We get, again, a packet received in a minimum size IO vector. Just something in the front that's going to remain in the user space. The rest, we'll see how it goes. It turns out that the header is a SMP3 transform header, which means that what's behind it in received packet is going to be encrypted. If it's encrypted, then, well, obviously, we need to decrypt it. So, again, another syscall. We're going to do that in a kernel. And the reason is because all the data remains in the kernel. So we need a syscall in order to say that, OK, we need to decrypt it. That's going to be one of the SMP3 encryption algorithms, of course. Obviously, given the information about the session, about the negotiated encryption algorithm, we need to set up a context that we're going to pass down the syscall to do the actual job. But again, the data encrypted is going to be decrypted in the kernel. So we don't have to touch it in the user space. We don't need to, for instance, use OpenSSL library and pull up everything, do the processing, and go over again. So we do the decryption, split off the transform header because at this point it's really no longer needed. Then we pull up the SMB2 header because the rest that we have in the kernel buffers are now regular. I mean, this is like unencrypted SMB2 traffic, so we just pull up the header. We get the header in the user space. The header says it's a change notify request. OK, if it's a change notify request, there's going to be no user data, realistically, in that request. So we can just pull up the rest of it. This is going to be the change notify request. And we are done. We have initially received something that resided mostly in the kernel space. But as we went through the processing of the entire packet, it turns out that we did not need to keep it in the kernel because everything that's about this request is going to be processed in the user space. So execute free, and we're done. So this means that the decryption and encryption, conversely, if we do the read from a file, can be done both of the user space and kernel space buffers. Because if you remember, with this kernel entry, the user space entry, the memory entry, when we pass it down to the syscall, it's going to be converted to the mbufs. That means effectively doing the copying. And with kernel space buffer, they're already there. So we have the entire chain of bytes that are linked together. They represent the packet that we are going to decrypt, so we can do it in one piece. And conclusion number 2, sometimes, and in many cases that's true, we just end up pulling up everything because effectively what we care about when it comes to zero copy is reading and writing. The rest, well, not really. I mean, most of those other cases are requests that we have to process in the user space anyway. So this is now this is where the present ends. This code is out there, it works, and it works fine. And by the way, I can tell you that doing that in the kernel space, the encryption and decryption with assembly code is pretty cool. Although reviewing that code is absolutely not cool. I've spent quite a while reviewing the assembly code doing the SMB3 encryption and decryption. But when you think of it, it makes perfect sense because the CPU instructions are all about simple incrementing, adding, byte shifting, things like that. And with the proper CPU extensions, which are very common these days, AES encryption, then it kind of really makes sense to do it using assembly. So it can be really fast if you use those hardware tricks that modern CPU provides. If even better, if you have specific drivers and hardware acceleration besides the CPU, then that means things get really even more interesting. But what's in the future? First of all, this is part of OneFS, which is based on FreeBSD, but it is not upstream FreeBSD, and I doubt that particular code would be upstream because it's too specific to OneFS. However, the concept itself could be implemented and upstreamed. Same applies to the Linux kernel. And I briefly looked at the Linux kernel code. How difficult would it be to do something similar in the Linux kernel? Okay. First, we have to deal with mbufs. If we have to deal with mbufs, which exist in the FreeBSD kernel, but they do not exist in Linux, then what's the equivalent? And if you try to look up over the internet using your favorite search engine, then many sources suggest that skbuf is the equivalent of mbuf in FreeBSD. Not quite so much. I mean, it does help and it does facilitate the IPC communication and network communication over BSD sockets. But if you look at the structure, instead of nice, tiny structure with pointer and data and possibly a few flags, there's a pointer to ICMP, TCP, some other state, and heaven knows what. So no, this is not the way to go. This skbuf is a lot bigger than it needs to be for this purpose. Not really useful for this kind of processing. So if we look deeper, then it turns out that IOV underscore ITER appears to be a bit more pleasant equivalent because it's similar to the concept of mbufs. Chained buffers, no connection actually with sockets whatsoever, but still that's what we care about. It's just a single linked list of buffers chained together, and that's it. And the interesting part of it is that also the BSD style user I/O header is in the kernel, in the Linux kernel, in fact, and it's been there for quite a while. So that's something that could be used. Of course, it would require syscalls, and I've already had a few conversations with Steve French and Matt about doing that. Trying to propose new syscalls, like 3 or 4. Well, at least I would have to. To be honest, I would like around 6 syscalls, completely new with the new functionality. That feels like starting a political campaign, but with an experimental code and a support with support from a few ioctls, and apparently ioctls are much easier to smuggle into the Linux kernel as an experimental code. Maybe this could be possible. So that's something that would be worth doing. Ideally, if Linux kernel received this kind of new syscalls, and then FreeBSD kernel received similar syscalls that would look the same, that would be ideal, but ideals are rare. So that would be even harder than the political campaign. I don't know, running for president probably. The next idea would be, quite obviously, RDMA and equivalence. If we have this struct file and we provide file obs that do certain smart and clever tricks on the chain of mbufs and that pretend to be a file, then why not try to do something similar, but this time just reach out to the RDMA-enabled device and provide another type of IOVEC entry that would be remote memory buffer, something copy offload, whatever. And using just different implementation of file ops for this structure over here. Let me. Oh, over here. Just with different file ops supporting this, and of course represented by an FD. That's the usual thing to do. We could potentially have a chance of having something close to standard way of doing remote memory access, remote RDMA effectively. And the positive thing would be that the work, for instance, that Matt's doing within the Samba team on RDMA and SMB direct support for that, it could be separated, it could be layered. You could use this kind of mechanism in order to reach out to the RDMA-enabled device and arm it with the SMB syntax, and there you go. So that's also something interesting to do. Perhaps this way of handling in-kernel and RDMA offload buffers, things like that, could be something that could be, I don't know, a recommendation how to do this and how to make this easier. Because then, if you employ the IOVEC-enabled syscalls that do the entire heavy lifting on your behalf, because you just read the IOVEC, save the IOVEC, receive that off the socket, then you don't really have to care so much about the specifics of the RDMA itself. Yes, I know I'm simplifying, but you see the idea. Yes, of course.
So what you're saying is if this comes into effect, then you don't need to do a registration of your buffer?
Probably not, because with those file ops that you implement and they can do anything, obviously it might require, for instance, a few IOCTLs on that FD so that you can prepare certain things. But then if the file ops, the functions that do the operations can do it for you, then you don't really need to. I mean, it's in a kernel implementation, so all you would care about in that case would be just reading of the socket to the IO vector, and the code that stands behind individual elements of the IO vector would know what to do. That's more or less the idea. Typically, yes, the life is a little bit more complex than that, which is why we have all sorts of IOCTLs that we need to pass on through the FDs and do all sorts of clever tricks. For instance, with decryption itself, before you even do the decryption or encryption in the kernel, yes, you have to set up the session key, you have to send all that data and initialize that state in the kernel, because it's going to happen in the kernel. If you even think of it, you have to start by setting up context. So probably it would require something similar. But then, once you are done, you just read, and that's what you care about. Okay, that would be it. And big credit to my colleague, Brian Koropov, who started the kernel side of this work. And ironically, this was started a while ago for the purpose of doing a similar thing on zero-copy signing. It is only until we've started working on SMB3 encryption project that I've looked at the code, because this was this special case for signing. I've looked at the code and why don't we just do it everything on IOVEX instead? Why does it have to be a special case just to enable zero-copy signing in the kernel? Well, we could handle that in the user space too. So here we go. Questions? Any questions? No, you're not allowed to ask questions. Mr. Hertel.
Besides, I think I got it.
Yeah. Well, we've talked about that before. Yes.
So how does it handle workloads? For example, you have both read and write at the same time with the entire chain of mbuf being in the kernel state?
Both read and write at the same time.
So you're, for example, in the same example you gave SMB, right? You're writing a large file, but at the same time, if the file is being read?
Oh, okay. Okay. So the question is how would you handle the other side of the operation simultaneously? Because simultaneously does not really occur in the SMB server. But how would the read look like? Yeah. What it's how it's built. Well, this time you get the request. You build the response. When you build the response, then you like in one of the earlier examples, you create a header, you get the data set in the header, you create the right response, and then you read from a file. If you read from a file using one of those syscalls, then you just create a kernel entry of certain size, which means asking kernel, please create a in-kernel buffer of this size for me. Do not send it to me. No, I don't need that. I just need an FD. Just reserve some space in the kernel, and then pass it to you pass it to the syscall doing read from a file, and the syscall doing this IO enable. Syscall does the read basically by looking at the FD. Okay, this is the file. This is the FD you've given me. Okay, so let's just take those blocks, detach, attach, and off we go. And you don't really even see it in user space. You get that. Attached to this pseudo-file in the kernel space that's still represented by the FD of the kernel entry, and then you get that it's still part of the IO vector, and you still have that FD. The only difference is that right now this FD points to a file that has those mbufs attached that you just read from a file, and they still exist in the kernel. So what you then do after you build the entire IO vector chain, you just pass it down to the syscall doing IO vector send response, and that one just gets the user space buffers. They are copied into mbufs in the kernel. The kernel space the entry does not have to be copied into the kernel, of course, because it's just an FD, so it points to the file. In kernel, you collect those mbufs and send them off. And once you have this chain of mbufs, it's sending them through the the BSD socket is exactly the same as it's done in the kernel right now. So that's it's only the matter of whether you get the data off the socket or you read it from a file. But effectively, it's still a chain of mbufs. Thank you.